Okay, so we've already verified that 4 of the axioms hold. The only thing that we need to check now is, does the field commute at space-like separation? By enforcing the 4 axioms that we have enforced, we've determined a lot about our field, its x-dependence and its momentum dependence. Everything is fixed up to a single arbitrary constant. Now, I'd like to start off by fixing that arbitrary constant. I'm going to fix it by making 2 observations. So the first observation is that, let me just change that. So the first observation is that we did not specify the strength of our field. And, this could be as simple as specifying the units that we're going to use to measure the field in. So we haven't specified what units we're using. If we choose our units correctly, we can set the magnitude of C to 1. So we can absorb the magnitude of C. All that we're left now is the phase. So the phase of C and C star. Next thing I want you to notice is that if you replace alpha k by e to the I phi alpha k, and phi is just a constant independent of k, and alpha p dagger into e to the minus I phi alpha p dagger. So I just daggered the first equation. That's why the e to the I phi became an e to the minus I phi. If you do this replacement, the commutators defining alpha and alpha dagger are unchanged. Okay, so what do I mean? I mean the last 3 commutators in the 5th axiom above, they're unchanged, and that means this is a symmetry. So we can change the phase of alpha without changing anything, and that means we can set the phase of C to 0. And that means actually we can remove C. So by a choice of units and a choice of phase for our oscillators, we are able to completely remove C from our formulas. So that gives us a slightly different mode expansion. Good. So now what I would like to do, I want to check the first axiom. So that means I need to calculate the commutator of phi of x with phi of y. So let's try to do that now. So we've got phi of x with phi of y. So what will that be? Well, let's put in phi of x. This will be an integral d3. Let's make it k1 over 2 omega k1, 2 pi cubed. There's the measure. Then we've got e to the minus I k dot x. We've got alpha k1 plus e to the I k dot x. We've got alpha dagger k1. And we're calculating that commutator with phi of y. And for phi of y, let's write integral d3 k2 over 2 omega k2 2 pi cubed e to the minus I. Sorry, this should have been a k1 and a k1. E to the minus I k2 dot y alpha k2 plus e to the I k2 dot y alpha dagger k2. And that's the commutator we want to calculate. Good. So let's get going with this. So the first thing that we can do is we can pull out the 2 integration measures. So we've got an integral d3k1 over 2 omega k1 2 pi cubed. And then we've got an integral, d3 k2 over 2 omega k2 2 pi cubed. So those are the two integration measures. And then we are calculating this commutator. E to the minus I k1 dot x1 dot x, sorry. Then we've got alpha k1 plus e to the I k1 dot x alpha dagger k1 comma e to the minus I k2 dot y alpha k2 plus e to the I k2 dot y alpha dagger k2. Okay, now we've done commutators like this before, where it's a plus b, commutator with c plus d, and we know that we should just multiply things out. So that's what I'm going to do now. So we've got an integral d3 k1 over 2 omega k1, 2 pi cubed, an integral d3 k2 over 2 omega k2, 2 pi cubed, and then we've got the first term from the two commutators. So we've got an e to the minus I k1 dot x minus I k2 dot y. And then we've got a commutator between alpha k1, alpha k2. Plus, then we've got the outer terms. So we've got e to the minus I k1 dot x and plus I k2 dot y, and we've got alpha k1 comma alpha k2 dagger. Then we've got the two inner terms, e to the I k1 dot x minus I k2 dot y, and it's a commutator between alpha dagger k1 and alpha k2. And then we've got the two last terms. This is e to the I k1 dot x plus I k2 dot y. And we've got an alpha dagger k1 comma alpha dagger k2. Good. Now, remember that alpha commutes with alpha, so that term over there vanishes, and alpha dagger commutes with alpha dagger, so the last term vanishes. So we've actually only got two terms left. And the commutator of alpha with alpha dagger is 2 pi cubed, 2 omega k times the delta function, and the commutator of alpha dagger with alpha is minus 2 pi cubed, 2 omega k times the delta function. So I'm just using the commutators that we had above, okay, in axiom 5. So we'll get an integral d3 k1 over 2 omega k1, 2 pi cubed. Then we've got an integral d3 k2 over 2 omega k2 over 2 pi cubed. And then we've got, so from this first commutator, 2 pi cubed, 2 omega k1. Then we've got a delta of k1 minus k2. And we've got the exponential of minus I k1 dot x plus I k2 dot y. Okay? And then we've got a minus 2 pi cubed 2 omega k1 delta of k1 minus k2, and we've got the exponential e to the I k1 dot x minus I, or is it minus I? Yes, minus I k2 dot y. Good. Now remember what K2 looks like. So K2 is a 4 vector. We've got omega K2, and then we've got K2 sitting there. So if we evaluate this at K2 is equal to K1, then we get omega K1, comma K1, which is K1 mu. So you see, even though the delta function only sets the spatial components of the momenta equal to each other, this is good enough to set the two 4 vectors equal to each other. So I'm going to integrate over K2 using the delta functions, and the delta function will actually set K1 as a 4 vector equal to K2 as a 4 vector. The other thing that will happen is that the 2 pi cubed and the 2 omega K2 will cancel against the measure for K2. Remember, K1 is set equal to K2, so the omega K1 will cancel against the 1 over omega K2. So integrating over K2, we're left with an integral d3K1 over 2 omega K1, 2 pi cubed. And then the measure has been swallowed up, and we've got e to the minus I K1 dot x plus I K2 dot y. Then we've got a second term. Oh, the second term is negative. And the second term is the integral d3 K1 over 2 omega K1, 2 pi cubed. And now again, this factor in front of the delta function will cancel against the measure, and we're just left with e to the I K1 dot x. Oh, sorry, guys. In the first term, this should have been K2 dot y because the delta function is set the k's equal to each other. Okay, good. Minus I K1 dot y. Good. Okay. Now, first thing I want you to notice, can you see that the coefficient of the delta function is also always cancelling against the measure factor for the integral of momentum? That's how we've chosen our 2 pi's nicely. All of the 2 pi cubes will cancel when you integrate over delta functions, so that's nice. And the energy factors will also cancel. Okay. Now, for this last term, just want to do a slight rewriting. Let me introduce the function delta of x minus y. Delta of x minus y is given by an integral d3p over 2 pi cubed to omega p. And then we've got e to the minus I p dot x minus 1. Okay? So I've just defined a function here. There's the definition of the function. And now take a look at my commutator. Now, the first term I can identify with a delta. It doesn't matter what we call the integration variable, okay? So the integral d3k1 could very easily be an integral d3p. Don't worry about that. So the first term here will be a delta. And it will be a delta of what? We've got minus I k1 x minus y. So we will indeed have a delta of x minus y. And then we will have minus, the second term is also a delta. It's exactly the same integral, but now it is minus x minus y, okay? So, okay, you could equivalently write it like this, x minus y minus delta of y minus x. That's the same thing, but that's the answer that we've gotten so far for our commutator. The next thing that I want you to notice about delta, so this is very interesting, we've got the exponential of p dot x minus y, and remember that p dot x minus y is p mu x minus y mu. So that's Lorentz invariant. The integration measure is also Lorentz invariant, so that means that this function delta of x minus y itself is also Lorentz invariant. Okay? So delta of x minus y is a Lorentz invariant. Good. We'll continue in a minute.